Wasabi, you guys. We have an unusual integral. This is not the typical integral that I would make on YouTube because it's one of these complex analysis integrals, or an integral that I've never shown before because I mean it's one of these famous integrals. Well, that's not the point. The point in this video is to show you to not always trust Wolfram Alpha, and one of the reasons that you have to be very careful about is very high oscillatory functions. So what I mean by that is, honestly I don't know what the graph of this looks like, but when you go to infinity, okay, and you have like a periodic function that goes like this, and it's gonna like high whatever, you know, because this is an increasing function, right? Yeah, I believe this is an increasing function. So what actually this is gonna look like, in a way, is it'll go like this, and then it'll start going crazy, crazier, and crazier, even here, and then whatever, right? So things like that. Computer programs, when they integrate functions like that, it cannot handle such values, and you know, as what people call it, hyper oscillations. It's gonna get an error. It'll give a numerical error all the time. I don't know about all the time, that might be an exaggeration, but a lot of the computer programs, like Wolfram Alpha, it cannot numerically compute correctly. So this, if you plug this into Wolfram Alpha, it's going to give you the wrong answer, in which case I have it right here. It's going to give you 0.6704, which is incorrect. Okay, and it's because this function with infinity, a hyper oscillating function, and infinity does not go well together with numerical approximations or numerical whatever the computer program does. Here, you have to be very careful. But how do we actually solve this? We can solve it ourselves, and we can find the exact answer of this. So let u equal e to the x minus 1. Right? You do a forced u-substitution. You get 2u du equal e to the x dx, which means that we have 2u u squared plus 1 du equal dx. You already know where this is going for all you advanced users out there, right? Plug in 0, we get what? 0 still. And plug in infinity, you still get infinity. And so what we have is 2u sine of u squared plus 1 du. And this is a famous integral, a very famous integral. So this is equal to like pi over 2e. So our answer would be like pi over e. Yeah, it's a very famous integral. Yeah, you see this a lot. The fastest way is to do residue theorem or complex analysis, but I know nothing about complex analysis, so contour integration is too hard for me. I can't wrap my head around it. It's too puzzling. I'm not very good with parameterization. So, but yeah, this is kind of the answer. It should be pi over e. Supposedly it should be pi over e. And so this integral here should equal to pi over e. Okay. For those who are interested in solving this, there's so many YouTube videos out there solving this, or this. Okay. There are so many videos. I think I have a integration bee training on like Laplace. It was like a very... Oh no, I'm sorry, it wasn't in Laplace. It was in advanced or like constructive Feynman techniques in the advanced integration bee series. It's like constructive Feynman, or like the last portion of the Feynman technique, where you have to use Laplace. Yeah, same with here. It's the exact same thing. You do like Laplace. It's nasty. But the fastest way to do it is complex analysis. But I don't know nothing about residue theorem, so I can't exactly teach you how to do residue dodging. Or maybe, I don't know, I'll consider. Maybe a future video. But it'll look bad on me because mathematicians would be so triggered, like, what, just learn residue theorem. Just learn it's not that easy, okay? It's not that easy. God. Okay, no one likes graphing. No one likes parameterizations. I'm sorry, but yeah, that whole complex contour integration is, you need to be comfortable with Calc 3 if you're not. Yeah, just good luck learning it. I can't. I'm still trying to learn it, but I'm struggling so hard. It's very puzzling. The whole point isn't to solve this though. I want to show you that to be very careful with Wolfram Alpha, right? Very hyper oscillating functions with infinity does not go well with numerical approximations with computers, so be very careful. Okay? Alright. I'll see you guys in the next video.